So beginning part one, the BlueGene hardware overview. So at ALCF, we have 3 BlueGene systems and a T&D, a visualization system, all of which share the same storage and same fabric. There's a second video conference which covers our newer Cray XC40 system with KNL processors. This entire session will focus mostly on the BlueGenes. Our main production resource is Mira, which has 49,152 nodes, or 786,432 cores, 768 terabytes of memory, a peak flop rate of 10 petaflops, and a peak Limpac flop rate of 8.1 petaflops. They're with the same configuration in terms of software and also shared directories and resources with Mira is a test and development system, CEDIS. It's 4 racks with 4,096 nodes or 65,536 cores, 64 terabytes of memory, and a 838 teraflop peak flop rate. On a completely separate fabric and storage infrastructure, there's a system called Vesta, which is our test and development system. It's 2 racks with 2,048 nodes, or 32,768 cores, 32 terabytes of memory, and a 419 teraflop peak flop rate. CEDIS and Mira and Cooley all again share the same storage. And Cooley, the visualization and data analytics resource, is 126 nodes or 1,512 x86 Haswell cores. Each node has a NVIDIA K80 GPU. There's a total of 47 terabytes of memory and 3 terabytes of GPU memory with a peak 293 teraflop peak flop rate. The storage that's shared between Mira, CEDIS, and Cooley. In Scratch, there's a 27 petabytes worth of usable capacity with an aggregate bandwidth to GPFS of 330 gigabytes per second. And then there's a separate home file system, which is 1.1 petabytes in storage with a 45 gigabyte per second bandwidth. I noticed there's a chat message.
I think it's me though.
Okay. Just checking. Again, if you have questions at any time, feel free again to either speak up or drop a message in the chat. So the ALCF resources slide kind of lays out how things are arranged. With Mira, CEDIS, and Cooley, again, all sharing file system resources. Our outbound connection to ESNet Internet 2 over 100 gigabits, and then the separate infrastructure for Vesta, the 2-rack open test and development system. The real split comes in that Mira, CEDIS, and Cooley are meant for users with Insight, ALCC, or large director's discretionary allocations. Whereas Vesta is, again, kind of like an open mic night. Anyone is welcome as long as they put in a proposal. The goal of these systems is that Vesta users are able to prepare and test code to see if they're interested in putting in a more detailed proposal for either ALCC or Insight down the line. BlueGene features. The chip inside the BlueGene is low speed, low power. It's an embedded PowerPC core, referred to as the A2 with custom SIMD floating point extensions. It works at about 1.6 gigahertz. We make up for the slow speed by having a large number of cores. So again, 786,432 cores on Mira. There's a very fast communication network in the form of a 5D Taurus network that provides around 44 gigabytes per second worth of throughput. Everything is well balanced between processor, network, and memory speeds. The operating system that we run on the BlueGene is a very lightweight operating system called CNK. CNK is Linux-like, but it is definitely not Linux. There are no remote logins. There are no shells. It's just purely the operating system and the user's binary alone out in memory. We provide certain standard programming models. Fortran, C, C++, and Python are all supported. I will throw out that the level of support for those languages is a little bit dated, but we'll come back around to that. We also provide MPI, OpenMP, and pthread parallelism, but there is no support for, say, OpenCL or OpenACC. The BlueGene nodes themselves are systems on a chip. It's a custom-designed ASIC. Everything is baked onto the chip with the exception of memory and just a little itsy-bitsy bit of EEPROM, which holds the node's serial number. This design greatly simplifies complexity and reduces power. It also kept down the cost per node, as opposed to a lot of systems. When BlueGene nodes die, we just throw them out or send them back to IBM for reworking. And the system is also designed for high reliability. And there's a highly sophisticated RAS system which tracks reliability, availability, and serviceability. Finally, because the nodes are low power and relatively low performance compared to Intel offerings, they're packaged in a very high level of density. So there's 1,024 nodes per rack. Briefly walking through the way that things are arranged within the BlueGene queue. Again, we've got the system on a chip, which is 16 cores plus 2. One is reserved for the operating system tasks, and one is a spare. Again, that's built into a module that's the full system on the chip, so all the communication bits, the CPU cores, the memory controllers, everything that would normally be spread out all over a PCB is in a single compact unit. That system on a chip is then on a compute card. The compute card contains 16 gigabytes of DDR3 memory, and the most prominent feature of it is a giant aluminum heat spreader for the water cooling. In turn, we take 32 of those compute cards, we put them onto what's referred to as a node board, and the node board is also carrying the link chips for the 5-dimensional torus. So that brings us to 32. Then we put 16 node boards together into a midplane. So that brings us to 512 nodes in a midplane. That's an important number to remember later on, because that's our smallest unit of allocation on Mira. And then we have 2 midplanes within a rack, again for 1,024 nodes in a rack. And then we arrange 48 racks of Mira together into the full 10 petaflop system. It looks like we may have another.
It's me.
Okay. Question. So we'll kind of go on. So that kind of gives us the overview of the compute, but the BlueGene queue system is more than the compute components. There's the front-end nodes. The front-end nodes are standard Linux boxes running Red Hat Linux. They're Power 7 systems. They're where users log in, you will compile codes, submit your jobs, check job status, debug applications, and basically conduct all the work of actually preparing and submitting jobs. There's additionally service nodes, and the service nodes are essentially appliances. They perform partitioning, monitoring of the compute nodes and compute racks. They are what's controlling the RAS system, and users generally do not interact with the service nodes except for indirectly. One unique feature of the BlueGene system is that there is no local storage on compute nodes. All of your I/O is forwarded. And there's a group of dedicated nodes referred to as I/O nodes, which are running Linux rather than CNK. And they are actually acting as a proxy between the compute nodes and the file systems. So every time you do any sort of basic POSIX file system call, whether that be read, write, stat, all of that is forwarded from the compute nodes by a daemon and executed on an I/O node on your behalf with the responses shipped back to the compute nodes. In general, we have one I/O node for every 128 compute nodes on Mira. the density is a little higher on Cetus and much higher in Vesta. And again, we've already mentioned the compute nodes, and that's where your user applications actually run. I had mentioned previously that there is no user access, and for the most part, it's a very low noise environment, just you, just your job and the operating system. Compute nodes are never ever shared. So one important thing to think about in the BlueGene case is partitioning. So the BlueGene queue, again, has a 5-dimensional torus. And rather than calling those dimensions X, Y, Z, W, V, instead, we label them A, B, C, D, and E. So the dimensions lay out the logical partitioning and dimensionality of the BlueGene 5-dimensional torus. Again, the smallest unit that we allocate on Mira is a 512 node partition, which is 4 by 4 by 4 by 4 by 2. And the largest possible partition is 49,152 nodes, which has dimensions 8 by 12 by 16 by 16 by 2. Other multipliers of 512 nodes are available. The supported ones are 1,024 nodes, 2048, 4096, 8192, 12,288, 16384. I believe we may actually have currently deactivated the 24,576 node partition and 32,768. So again, the traditional kind of powers of 2 blocks are how we allocate. I'll note that Cetus and Vesta have a higher IO node density, and so we support smaller partitions on Cetus and Vesta. The smallest one available on Cetus is 128 nodes with a dimensionality of 2 by 2 by 4 by 4 by 2. And the largest possible partition is 4096, which is generally not active, but is 8 by 4 by 8 by 8 by 2. And then on Vesta, the smallest possible partition is 32 nodes with a dimensionality of 2 by 2 by 2 by 2 by 2, or a single node card. Again, where the Mira partitioning comes in important, again, is this is how we wind up allocating pieces of the system. The pieces that are outlined show the node count within different partitions. So a 512 node partition is, again, a midplane. 1024 gives you a rack. 2048 is 2 racks. 4096 is 4 racks, but you'll notice that they're spaced out. While it's not contiguous in a Cartesian system, it is contiguous and a full torus within the 5-dimensional torus network. The next kind of block size up is 8,192, which is in 8 contiguous racks. And then 16,384 nodes, which is a full row of Mira. There is a very important page and that a lot of users find very valuable, which is the Gronculator, which is available at status.alcf.anl.gov/Mira/activity. And it will show you who is running and where on the system and which blocks are free. It also will give a list of queue jobs and upcoming reservations. The other similar command from the command line is partlist, which will show you if a block is free or busy, and if it's blocked, if it's blocked due to a wiring dependency or downed hardware. So again, the minimum partition size on Mira is 512 nodes, on Cetus 128, and Vesta 32 nodes.